In this video, we'll look at integrating factors with respect to first-order linear differential equations. So, what is a first-order linear differential equation? Well, from the definition of linearity of a differential equation, a first-order linear differential equation is of the form a1 dy over dx plus a0, okay, meant right, a0 y equals fx. So a1 and a2 are functions of x, or they can be constants. That still is a first order linear differential equation. Fx is obviously a function of x for this to be a valid first order linear differential equation. So in this kind of differential equations, the first order linear differential equations, we'll look at a shortcut method of finding the integrating factor as opposed to the analytical method where we have to do a lot of inspection to find what the integrating factor is. So let me write this differential equation in a rather more easier way. I'll divide by a1, so I'll have dy dx plus a0 divided by a1 times y equals fx over a1. So I'm going to let me set some values here. I'm going to let a0 over a1 to be equal to p. Also, I'm going to let this fx, so I'm going to let fx over a1 to be equal to q. So let me write this differential equation as dy dx plus p y equals q. So every time we apply integrating factors to first order linear differential equations, we've got to make sure they are in this special form. This is very important. If we do not apply the integrating factors to this special form, then it won't work out. This is very important. It's a special form of first order linear differential equations where we can easily find the integrating factor and we apply it to work. So after expressing our first order linear differential equation in this form, the integrating factor is going to be given by, let's call this integrating factor r for simplicity. So the integrating factor r is going to be given by the exponent of the integral of p, this p here, with respect to x. So I'll prove this at the end of this video. So the proof for this at the end of the video. So for now, we'll apply this formula to find integrating factors and solve a couple of examples, and then we'll end the video by proving why this integrating factor method actually works. This formula for finding the integrating factor. Okay, let's go ahead and look at some examples. So let's have some examples. First one, we have dy over dx plus 3y equals exponent, what's that going to be? That's exponent 2x. Okay, so notice that this equation is already in the special form dy dx plus py equals q. Q is a function of x, that's obvious. So there we have dy dx, then we have our p as 3, and then there we go. So we can easily find the integrating factor since we already have p. We already have the same form of equation here. So the integrating factor integrating factor, we call that r is going to be exponent of the integral of p with respect to x. So that's the exponent of the integral of 3 with respect to x, and that's going to be exponent 3x. Notice that we set the constant to be 1, so we just leave this as our integrating factor. So after getting the integrating factor, remember by definition an integrating factor is a term that we have to multiply throughout the equation to make it exact. So let's multiply this original equation by the integrating factor, multiply by exponent 3x. Let's go ahead and do that. So we'll have exponent 3x dy over dx plus 3y times exponent 3x equals, if we apply the integrating factor here, we'll have, if we multiply by exponent 3x, that becomes exponent 5x. From the laws of indices, a to power n times a to power m, I think that's a to power n plus m. Yeah, some kind of elementary algebra. Okay, there we go. So let's see, let's form an exact differential. We are sure that after multiplying the equation by an integrating factor, then we can actually make an exact differential out of it. So let's see what this exact differential is going to be. Perhaps y exponent 3x. Why do I choose this? Because I see there is exponent 3x that was kept constant here, and then dy dx is actually the derivative of y. And then also looking at this term, I see if I keep y constant, the derivative of exponent 3x is actually this 3 exponent 3x. So this is the exact differential for this. Okay, I'll equate that to exponent 5x. So you can try this out to find the derivative of this using product rule. You should be able to see that this is actually the same as what we have here. Okay, so I now take this dy exponent 3x, this as exponent 5x dx. Let's take integrals. So the integral of dy exponent 3x, the integral of exponent 5x dx. So this is going to be y exponent 3x equals the integral of exponent 5x, that's 1 over 5 exponent 5x plus some arbitrary constant. Let's call that a. Okay, this is a good one. Whenever possible, you could try to express the final general solution in terms of x. So let's try that out here. If we divide through by exponent 3x, y is going to be equal to 1 over 5 exponent 2x plus a exponent negative 3x. So of course a over exponent 3x is a exponent negative 3x. So that's why we're having this as our final solution, the general solution to this differential equation. We can go ahead and find the particular solution if we are given some initial conditions. So in case we have initial conditions, let's try that out. Let's suppose we have the initial conditions y of 0 equals 6 over 5. Let's find the particular solution. Let's find the particular solution in this case. Of course, y 0 equals 6 over 5 means, if I could write this solution is y as a function of x. So y 0 means, okay, let's just write this like this, y x, so y0 equals 6 over 5 basically means the value of y is 6 over 5. The value of y is 6 over 5 when x is 0. So those are the initial conditions. Let's apply them here. So we'll have y as 6 over 5. Let's put the conditions here. Have 6 over 5 equals 1 over 5 exponent 0. Now the exponent of 0 is actually 1. Then plus a. Of course, also exponent 0, which is 1. Exponent 0 is 1. Okay. So let's take 1 over 5 this side with some little algebra here. We'll have 6 over 5 minus 1 over 5, and that's going to be 1. So our particular solution is, at this condition of x0 when y is 6 over 5 is going to be y equals 1 over 5 exponent Okay, let's have another example. So let's have a second example here. Dy dx plus 2xy equals x. Also notice that this is already in the form of dy dx, dy over dx plus py equals q, the function of x. So in this case, you can easily see that p is actually 2x. There we go. So our integrating factor, r is going to be the exponent of the integral of 2x dx, which is the exponent of x squared. So there we go. Let's multiply the equation, the original equation, which is in this form, by the integrating factor. So let's see, we'll multiply by the integrating factor by exponent x squared. So what we have here, we'll have exponent x squared dy dx plus 2xy exponent x squared equals x exponent x squared. So let's try to form an exact differential here. So that's going to be, what's that? Y exponent x squared. I guess that's going to be because in order for us to have this, you can see that exponent x squared was kept constant, and then the derivative of y is dy dx. Also here, if we keep y constant, the derivative of exponent x squared is actually 2x exponent x squared. So there we go. This is equal to x exponent x squared. So let's write this, dy exponent x squared equals x exponent x squared dx. If we take integrals on both sides, so integral here, we'll have y exponent x squared equals, so what do we have on this side? I don't want to do this integral, but you could actually use a technique here called change of variable, and so that's one of the techniques of integration. Using that technique, I guess you will find the result as 1/2 exponent x squared. Okay, let's try to do it. Not okay. So let's try to do this integral of exponent, okay, x exponent x squared, x squared dx. So I will let u to be equal to exponent x squared. And then what do we have here? So du dx, is that a good choice? Okay, that's a function and its derivative. Du dx is going to be 2x exponent x squared. So let's try to replace that with dx. So we'll have the integral of x. Exponent x squared is actually u, so times u. Then dx, from here, dx is actually du divided by 2x u. Exponent x squared is u, so you can see that x cancels out, u also cancels out, and then we have the integral, a half, can pull that outside, a half du, which is going to be a half of u, and u is exponent x squared, so that's a half exponent x squared. Okay, that's a nice one. So this, forgot to add a constant here. Let's do that. Let's add a constant here plus c, an arbitrary constant. So this is the general solution to our differential equation. I think we can make this actually look better if we express it in terms of x. That's going to be a half plus c exponent negative x squared. Okay, this is better. So that's our general solution to the differential equation. Let's take another example, number 3. Let's take dy dx plus y plus 3 equals to x. Remember, for us to use the integrating factor on a first order linear differential equation, it must be of the form dy dx plus py equals q some function of x. So this differential equation does not match the criteria yet. Let's try to rearrange the terms to make it match the criteria. So I'll write as dy dx plus, I only need p y on the left hand side, so for that case I only have 1 times y, and then I take everything else that cannot be together with y on the right hand side. So that's going to be x, I guess, minus 3. Yeah, it's a positive, minus 3. So if I compare this equation with this, you notice that p is actually 1. So p equals 1. So my integrating factor r equals exponent, the integral of 1 dx, and that's going to be exponent x. So let's multiply this equation here by the integrating factor. Notice that we do not multiply by the original equation, but we multiply by the equation that matches the format that we want, the format of dy dx plus py equals qx. Okay, so I'll multiply by the integrating factor exponent x. What do we get? Let's do that. This is going to be exponent x dy dx plus y exponent x equals exponent x into x minus 3. Let's try to form an exact differential from the left hand side, d dx of what do you think the exact differential here is? If you look at the terms on the left hand side, exponent x was kept constant, and then the derivative dy dx is the derivative of y. Also, from the next term, if we keep y constant, the derivative of exponent x is exponent x. So this is it. We could expand that to prove that it is indeed the exact differential. So this equals exponent x into x minus 3 d of exponent xy equals exponent x into x minus 3 dx. So let's take integrals on both sides. Integral of d exponent x times y equals the integral of exponent x minus 3 dx. Okay, so how do we deal with this integral? Well, so let's just do that on a side. Only this integral here, that's going to be the integral of exponent, that's going to be x exponent x minus 3 exponent x dx. Okay, so we just expand this out, and this is kind of tricky. So to solve this integral here, you'll need to use a technique called integration by parts. Integration by parts. Okay, so using integration by parts, you can find what the integral here is. This is easier. We know the integral of exponent x is exponent x itself. So I'll just show you the final result here because I don't want to make the video too long by finding all the integrals. So, okay, let's just continue now to solve the differential equation. So this is going to be exponent x. Okay, let's get another color here. That's going to be exponent x times y equals this integral here. After finding the solution, you'll find that the integral to this is actually x exponent x minus exponent x. That's the integral. Then the integral of that is 3 exponent x. It remains the same. So that's what we have here. Of course, if I combine these two, I'll have x exponent x minus 4 exponent x. So x exponent x minus 4 exponent x plus an arbitrary constant. Could call that constant k. There we go. If I divide through by exponent x, just extend this up a little bit. If I divide through by exponent x, I'll have y as x minus 4 plus k exponent negative x. So this is better. This is our general solution to the differential equation. Okay, it's nice. Let's have another example. That's example 3. Let's have example 4. Okay, so let's find the general solution of the differential equation dy dx minus y over x equals x squared, where x is greater than 0. Then we'll go ahead and find the particular solution subject to these conditions. Okay, so let's write our differential equations. Dy over dx minus y over x equals x squared. I'll compare this with our general form, dy dx plus py equals q, a function of x. So by comparison, you can see that p is negative 1 over x. I could write this as y times 1 over x, so negative 1 over x. That's our integrating factor. Sorry, that's our value of p. So I'll use that to find the integrating factor. So the integrating factor, let's call that r. is the exponent of this p, the exponent of the integral of p dx. So the exponent of the integral of negative 1 over x dx. Let's go ahead and see what this is. This is exponent of negative natural log of x. I could write this as exponent of negative, exponent of natural log of x to the power negative 1. Yeah, that's from the laws of logarithms. But of course, this is the antilog of the natural logarithm. So I just write this as x to power negative 1, or more specifically 1 over x. So I'm going to multiply this. Let's go ahead and multiply this by 1 over x. In that case, we'll have 1 over x dy dx minus y over x squared equals x. Let's try to form an exact differential equation from that. So let's have d over dx of, so 1 over x and then dy dx. What is the exact differential for this? You realize that here y is kept constant and the derivative of 1 over x is negative 1 over x squared. So this is likely to be y over x. If you try to, okay, let's do it. So if I keep 1 over x as a constant, the derivative of y is dy dx minus, if I keep y constant, okay, the derivative of 1 over x is 1 over x squared. Okay, there we go. So this is our exact differential. Let's replace it here. So we have d dx of y over x. d dx of y over x is going to be equal to x. So d of y over x equals x dx. If you take integrals on both sides, this is going to be, okay, let's do that. So we have y over x, y divided by x equals x squared over 2 plus some constant k. Could write this as y equals x cubed over 3 plus kx. So there we go, that's our general solution. So notice that here I should have actually said negative natural log of the absolute of x, but I only said x because x was greater than 0 from this condition. So instead of saying absolute, I just said this x, because x is already a positive value, it's greater than 0. Okay, so here we have a general solution. Let's go ahead and find a particular solution subject to those conditions. So I'll pull this over. Okay, so let's go ahead and find a particular solution for the condition y0 equals, what's that? Sorry, y1, y of 1 equals to 0. So that means x is equal to 1 when y is 0. Let's substitute that here. We'll have, when y is 0, x is 1, so we'll have 1 over 3 plus k. So k is 1 over 3. There we go. Let's put back the value of k here. In that case, we have y equals x cubed over 3 plus x over 3. I could just write that as 1 over 3 into x cubed plus x. Oops, I think I could just say right away from here, I could say x over 3 into, I think this could be better, into x squared plus 1. So this is much better. This is our particular solution subject to this condition here, to this initial condition. Okay, let's have another example. Let's just check here. This is example 4. So let's have example 5. Let's have example 5. Okay, so let's find the general solution to the differential equation cos x dy over dx plus sin x times y equals 1 at, given this condition has to be valid, and then we'll go ahead and find the particular solution at this condition. So let's first find the general solution. We have our equation cos x dy dx plus sin x times y equals 1. As you notice, this is not compatible with the general form dy over dx plus py equals qx. So let's try to make this look like this equation, to express it in the general form. I'll divide by cos x throughout the equation. So I'll divide through by cos x. In that case, we'll have dy dx plus sin x over cos x is going to be tan x times y. 1 over cos x is going to be sec x. So let's find the integrating factor here. So if I compare this, so if I compare these two equations, you can see that the value of p is actually tan x. So our integrating factor r is going to be the exponent of the integral of tan x, which is going to be, okay, so what's the integral of tan x? That's the integral of sin x over cos x. That's negative natural log of cos x, which is the same as natural log of cos x to the power negative 1. And you know, 1 over cos x is actually sec x. So instead of writing this, we could write natural log of sec x. Okay, so let's just take off this. Just wanted to show you how that comes. So this is going to be natural log of the absolute, let's use a different color, the absolute of sec x. So r is going to be the natural log. Okay, is that right? I guess this isn't okay, that's sec x. There's an exponent missing here, so that's going to be exponent. Okay, the exponent and the natural log cancel out, so this is going to be the magnitude of sec x. But you see, we have a condition of this. We have a condition that x ranges from 0 to pi over 2, and for this region, for this range, then sec x is always going to be greater than 0. It's always going to be a positive value. So my integrating factor is going to be sec x. I don't need the absolute value, because in the given range, I know that sec x is always going to be a positive value. So let's go ahead, keep this now in mind. I'm going to clear this screen, and then I use the integrating factor. Notice that I will multiply the integrating factor here on this equation, not in the original equation, because the original equation does not match this special form. So the integrating factor is r sec theta, sorry, the integrating factor is sec x. Okay, so let me clear this out. Then so I multiply this by sec x. Let's see what we have. This is going to be, so I multiply by sec x, that's going to be sec x dy dx plus tan x. Alright, so that's sec x tan x times y. On the right hand side we'll have sec squared x. So what's the exact differential for this? So this is kind of interesting. This is d over dx of y sec x. Guess that's it. The derivative of y is dy over dx, sec x being constant. The derivative of sec x is sec x tan x, so that's okay. There we go. And then the other side we have sec squared x. So let's go ahead and separate variables. D of y sec x equals sec squared x dx. So after separating variables, I'll take integrals. On both sides we have y sec x equals, what's the integral of sec squared x? That's tan x. That's tan x plus constant, let's call that constant a. If we actually divide by sec x, let's see what we shall have. Y equals tan x over sec x plus a over sec x. Tan x, remember tan x is actually sin x over cos x, and then sec x is 1 over cos x. So this is going to become sin x. Yeah, guess that's going to be sin x plus a cos x. So this is our general solution to the differential equation. So let's keep that, and we apply the given conditions to find the particular solution. So let's go ahead and do that. Particular solution. Particular solution at y0 equals 1. So we already know the general condition. The general solution is sin x plus a cos x. So let's put in y equals 1 when x is 0. So we have sin 0 plus a cos 0. So sine of 0 is 0 and cos of 0 is 1. So a equals 1. So our particular solution then becomes y equals sin x plus cos x. And there we go. That's our that's our particular solution to this differential equation. Okay, so it's kind of a nice one. Okay, let's have more interesting problems. Let's try this out. What's this? This is problem number 5. Let's take problem number 6. This is going to be x dy dx plus 2y equals cos x. Okay, good. Let's try to see if this matches the form dy dx plus py equals q x. So notice that it does not match, so let's try to rewrite that as dy over dx plus 2y over x equals cos x. Is that going to be, yeah, cos x divided by x. Okay, that's a good one. Let's see what's the value of p, this one here. I guess you can see this, that's the value of p. So our integrating factor, which is given by the integral of p, the exponent of the integral of p dx, in this case is going to be exponent of the integral of the value of p, in this case is 2 over x dx, that's the exponent of natural log of x squared. So the integrating factor is x squared. Now let's multiply here this equation. So multiply by x squared. We do not multiply the original if it's not in this format of the general form that we need. So let's multiply here by x squared. What do we get? X squared dy dx plus, what's that? 2xy equals x cos x. Okay, the exact differential is going to be, I guess that's x squared y. Yeah, the integrating factor makes the exact differential so obvious to find. On the right hand side we have x cos x. We separate variables. It's going to have x cos x dx. If I take integrals on both sides, the integral of x cos x dx, this is going to be x squared y. Again, we can only integrate this using the technique of integrating by parts. Yeah, I guess so. Let's just do this independently. The integral of x cos x, let's try that. The integral of x cos x dx. So integrating by parts, you know that the integral of u dv dx with respect to x is equal to uv minus the integral of v du dx with respect to x. So I'm going to let, what should I let? I'm going to let u to be equal to x. So that basically means du dx is actually 1. Then I also let dv dx to be cos x. So in that case we have dv equals cos x dx, and v is going to be the integral of cos x dx, which is actually sine x. Okay, let's substitute this and this into this equation. So we'll have the integral of x cos x equals u is x, v is sine x, minus the integral of v, which is sine x, du dx is actually 1, and there we have our dx. So this is x sine x minus the integral of sine x is negative cos x. So I could just write this as plus cos x plus some constant k. There we go. So I'll transfer this to the previous question. So our answer here becomes x sine x. Guess I'm getting this right. X sine x plus cos x plus a constant k. So there we have our general solution to this differential equation. Okay, so let's try to do more examples here. Okay, perhaps this. That was problem number, what was that? That was number 6. Okay, let's do problem 7. Just get an interesting one here. dy dx plus 2y equals exponent negative 2x times cos x. So let's try to solve this. It's already matching the form of dy dx plus py equals qx, and you notice that p is actually 2, so the integrating factor r is going to be the integral of the exponent of the integral of 2 dx. That's exponent, what's that? Exponent 2x. Then I multiply here. It's already matching this criteria, so I'll just multiply that. Multiply by exponent 2x. Okay, that's going to become exponent 2x dy dx plus 2y exponent 2x equals cos x. So exponent 2x times exponent negative 2x is actually 1. So there I have cos x. The exact differential for the left hand side is going to be y exponent 2x. If you try this out, so exponent 2x, if you keep that as a constant, the derivative of y is dy dx. 2y exponent 2x, the derivative of exponent 2x is 2x. Okay, there is an x missing here. Is that so? I guess no, there is no x missing. Yeah, the derivative of 2x is actually 2, and then 2 exponent 2x, and then y. Yeah, so that's it, equals cos x. Let's separate variables. This is going to be cos x dx. I take integrals on both sides, equals the integral of cos x with respect to x. So y exponent 2x is going to be equal to the integral of cos x is sine x plus some arbitrary constant. Let me call that constant g. So there we have our general solution to this differential equation. Let's take more problems. 8. Let's take dr d theta plus r tan theta equals cos theta. Okay, this is already of the form, what should I say, dr d theta plus pr equals q as a function of theta. Yeah, so it's already in this format. So notice that p is actually tan theta. So the integrating factor is going to be, let's call that r, the exponent of the integral of tan theta. What's that? Exponent of, that's natural logarithm of cos theta. I guess tan theta is sine theta over cos theta. That's going to have a negative here. That's exponent of natural log of cos theta to power negative 1. That's same as natural log of sec theta. So the antilog here cancels with the natural logarithm, so we have sec theta. I'll only take values of sec theta greater than 0, so I don't need to deal with the magnitude here. We'll just take a simpler case. Let's multiply this multiply by sec theta. See what we're going to have. That's going to be sec theta dr d theta plus r sec theta tan theta equals cos theta times sec theta is actually 1. So the exact differential here is going to be r sec theta equals 1. If we separate variables, r sec theta equals dr. I take integrals on both sides equals the integral of dr. So r sec theta equals r plus a constant c, and there we go. That's our general solution to this differential equation. Okay, that's a nice one. That's problem 8. We'll take about 2 more problems. Let's take another one. 9. Let's take this is going to be dy dx plus 2 x plus 1 times y minus exponent negative x squared equals 0. So let's do some rearrangement here. I'll write this as dy dx plus 2x plus 1 y equals exponent negative x squared. This is better because it looks like our general form, which is this. So p is actually 2x plus 1, and our integrating factor is going to be equal to the exponent of the integral of 2x plus 1 dx. That's going to be the exponent of x squared plus x. So I multiply this with the integrating factor exponent of x squared plus x. Let's see what we'll have. In that case, have exponent x squared plus x dy dx plus 2x plus 1 exponent x squared plus x times y. On the right hand side, we'll have exponent x, because exponent x squared plus x times exponent negative x squared, yeah, you get the idea. This is elementary algebra in indices, so you can expand the indices there and you'll see this come out very easily. So let's find the exact differential. The exact differential here is going to be y exponent x squared plus x. On the right hand side, we have exponent x. If we separate variables, have this. I'll take integrals on both sides. So y exponent x squared plus x equals the integral of exponent x is exponent x plus a constant k, an arbitrary constant, and there is our general solution to this differential equation. Let's take another example. That's going to be number 10. Let's take which one? Let's take this, dr d theta plus 2r cot theta equals cosec theta squared. So this is already in the form dr d theta plus p r, guess that's it, equals q theta. You notice that p is actually 2 cot theta. Guess that's it. So the integrating factor r is going to be the exponent of the integral of 2 cot theta, and if you do the math, you'll get this as sine squared theta. Let's try to do this slowly. That's the integral of, so the integral of cot theta is actually natural log of sine theta, and from the laws of logarithms I can take the square here, so that becomes sine squared, and when I apply the anti-logarithm, there we go, sine squared theta. So let's multiply this. Let's multiply with sine squared theta. In that case, we'll have sine squared theta dr d theta plus 2r. Okay, so we have cot theta sine squared theta equals 1. Cosec squared theta times sine squared theta is 1. Let's try to see what's cot theta sine squared theta. I guess that's also simplifiable. So dr d theta, there we go, plus 2r. Cot theta is cos theta over sine theta times sine squared theta. Okay, so this is, you know, this cancels here. This is cos theta sine theta. Okay, so let's take this off. We'll have cos theta, cos theta sine theta equals 1. The exact differential for this is going to be ddr of r sine squared theta. On the right hand side we have a 1. If I separate variables, r sine squared theta equals dr. Since I don't have much space, let's take integrals here on both sides. So we have r sine squared theta equals r plus a constant. Let's call that constant b, and there we have our general solution to this differential equation. So I guess that's enough examples. We could have done more, but I don't want to make the video too long. So we'll now end the video by looking at a derivation of the formula for finding the integrating factors. Let us see how we can find an integrating factor specifically for first order linear differential equations. We are looking at only the ordinary type. So how to find an integrating factor for first order linear differential equations. Now with me here I have the general form of a first order linear differential equation, a1 dy over dx plus a0 times y equals to some function of x. Of course, in this case a1 cannot be 0, otherwise the differential equation is not first order. In fact, it won't be even a differential equation. So there we go, a1 and a0 are presumably functions of x, or they can be constants. Fx is a function of x, that's obvious. So let's see how we can find an integrating factor for solving such a first order linear differential equation. Now the first step here, is to write the differential equation. Write the differential equation in a special form, and we're going to see what that special form is. So let's take this very genoform of a first order linear differential equation. I'm going to write that as dy dx plus a0 divided by a1 times y equals fx divided by a1. So what I've done here is divide throughout the whole equation by a1, and then let's write this as dy dx plus py equals q, a function of x. In this case, I have let a0 over a1 to be equal to p, fx over a1 to be equal to q, function of x. Okay, so this is the first step. We write the differential equation in this special form. Here we go. Let's carry this forward to the next step. This is very crucial before we can use the integrating factor method. Our differential equation is going to be written in this form. Now let's go to the second step. The second step, let me begin by letting r to be my integrating factor. So let r be the integrating factor. So if r is the integrating factor, that means I can multiply throughout the equation to make it exact. So let's write a small note here. We can multiply this equation here, dy dx plus py equals q of x. This equation here, we can multiply this by r to make it exact, assuming it was initially not exact. So we multiply it by the integrating factor r to make it exact. Let's see what we shall have in that case. If I multiply this equation by r, that's going to be r dy dx plus p, that's going to be r py equals r q, a function of x. I'm going to call this equation 1. Now obviously r must be chosen. So r must be chosen such that, so we have to choose an integrating factor that will make the left hand side of this equation to be an exact differential. So r must be chosen such that all the left hand side, which is r dy dx plus r py, is the same as d over dx of ry. This condition is necessary because r is an integrating factor, so it has to make this left hand side to be an exact differential. So let's see what this is. D dx of ry, that's going to be, what's that? That's oops, we've got ry here. That's going to be r dy dx plus y dr dx. Let's call this equation 2. Okay, just create a little bit more space here. Okay, there we go. So let's compare equation 1 and 2. So there we go. We compare equation 1 and equation 2. I'll rewrite both equations here. So equation 1 is r dy over dx plus r py equals r q of x. Okay, so let's compare that with equation 2. That's r dy dx plus, okay, what do we have here? Y, is that y? Yes, dr dx equals, of course, this, the differential of ry with respect to x is the same as rq because we got this from here, from equation 1, so that's reasonable. Now by direct comparison, this is the same, the first term. That means the second term also has to be equal, since the last term is equal. So let's do that. That means these two terms must be equal. Y dr dx is going to be equal to r p y. You notice that y cancels immediately. We have dr dx equals r times p. Okay, let's just have a little bit of space here. In this case, we can separate variables. So let's separate variables and see what we get. This is going to be dr divided by r equals p dx. So I'll take integrals right away from here on both sides. So we have natural log of r equals the integral of p with respect to x. So if I put exponents on both sides, which is the antilog of the natural logarithm, I'll have r equals exponent of the integral of p with respect to x. This formula here is used to find the integrating factor for first order linear differential equations.